Welcome back to the Explainer. We're jumping right into episode 1.3, part 2, self and mutual inductance. In the first part, we uncovered a pretty massive rule of the universe. Changing magnetic flux creates voltage. We actually saw how physically moving a magnet near a coil induces an electromotive force. But today, we're looking at a scenario that's honestly even more fascinating, because it's the hidden engine driving almost all modern electrical machinery. What happens when you put the magnet away, and instead a coil just changes its own current?
So here's the crucial takeaway right up front. A coil's flux can change simply because its own current is changing. It acts a whole lot like, magnetic inertia. See, when current flows through a wire, it creates a magnetic field. If you ramp that current up or down, the magnetic field expands or collapses. And because that field is expanding or collapsing right across the coil's own wires, it induces a voltage in itself. It's wild, but this one single phenomenon literally changes everything about how electrical machines behave in the real world.
Okay, let's build up the math that makes this happen, step by step. First up, we've got flux linkage, which we represent with the Greek letter lambda. That is simply N, the number of turns in our coil, multiplied by the total flux, phi. And that's the flux threading through all those turns, not just a single loop. Next, we define self-inductance, or L, which is measured in henries. This is just your flux linkage divided by the current producing it. Now, because that flux changes whenever the current changes, a coil induces a voltage in itself. That leads us right to our third formula, E equals L times di over dt. So what does that mean in plain English? It means the self-induced voltage equals your inductance multiplied by how fast that current is changing. Because of this, coils fundamentally resist sudden changes in current. The faster you try to change it, that super steep di over dt, the harder the coil pushes back.
Now, let's take this concept and level it up to what I honestly consider the superpower of induction. Mutual induction, denoted by M. If we bring a second, totally separate coil close to the first one, the expanding and collapsing magnetic flux from coil 1 will actually sweep right across the wires of coil 2. The induced voltage in that second coil becomes M times the rate of change of current in the first coil. Think about that for a second. We are literally inducing voltage across empty space.
And this brilliantly illustrates how a real transformer core operates. You've got a primary winding on one side and a secondary on the other. A changing AC current in that primary winding creates a changing magnetic flux. That flux travels right through the iron core and links up with the secondary coil. It induces a voltage in the secondary purely through that shared flux, with absolutely zero electrical connection between the two sides. It is just an incredibly elegant way to transfer power.
But, as with most things in physics, this reality acts as a very real, very dangerous double-edged sword. We just established that inductors mathematically resist changes in current. So what do you think happens if you take an active inductive circuit like a heavy relay coil or a motor winding and you suddenly snap a switch open to turn it off?
Let's walk through the sequence of exactly what happens. Step 1, the switch opens. Step 2, you are forcing the current to drop to zero instantly. Mathematically speaking, your di over dt, your rate of change, is shooting toward infinity. Step 3, right on cue with our formula, the self-inductance fights that sudden drop with everything it's got. It desperately wants to keep that current flowing. And step 4, this generates a massive voltage spike, easily thousands of volts, which physically tears through the air and bridges the gap of your switch as a highly destructive arc of plasma.
So, time for a quick check. I want you to actively apply what we've been talking about. Imagine you're watching a relay coil operate. It gets de-energized, you hit the switch, and a small, bright orange spark appears right at the mechanical contacts. Based on the physics of E equals L times di over dt, what exactly caused that spark? Take a second and think about it.
Well, the answer is the coil's stored magnetic energy violently collapsing. See, turning the relay off collapses the current suddenly. The spark you are looking at is quite literally the physical manifestation of self-inductance fighting back against that collapse. The magnetic field is rapidly dumping its stored energy right back into the circuit, and that spikes the voltage high enough to just jump the physical gap you just created.
Now, what's really fascinating is how engineers actually tame this wild voltage kickback out in the real world. The danger is constant arcing, which destroys delicate relay switches or, even worse, blows out incredibly expensive transformer bushings. So the solution? We give that collapsing magnetic energy a safe place to go. On smaller circuits, you'll see flyback diodes or snubber circuits wired right across the coil to gently dissipate the spike.
But on massive utility transformers, engineers use surge arresters or sacrificial arcing horns. These are metal points that deliberately give the arc a safe place to jump in the open air, literally saving a $50,000 transformer from a sudden inductive surge.
And this inductive kickback, it isn't just a problem for switches. It causes massive headaches inside spinning machinery too. In DC motors, for instance, there's a phenomenon known as armature reaction. When a motor is running under a heavy load, the magnetic field from its own spinning armature, the rotating coil, actually distorts the main magnetic field of the machine. This physically shifts the motor's true neutral zone, which is that safe spot where the carbon brushes are supposed to sit so they avoid sparking.
If those brushes aren't in that exact neutral zone, they end up short-circuiting coils that still have voltage in them. And because of the coil's self-inductance, that rapid short-circuiting causes severe sparking right at the brushes, which can completely burn them up. To combat this, machine designers implement commutating poles, or interpoles. These are small secondary electromagnets placed right between the main poles. They automatically cancel out the armature reaction and provide the exact voltage needed to overcome the coil's self-inductance. That ensures smooth, spark-free commutation even when the machine is under a really heavy load.
So, you came into this explainer knowing that changing flux makes voltage. Now, you understand the deeper mechanics. You know exactly how a coil's own changing current creates that flux, how two coils couple together to create a transformer, and the invisible, sometimes super destructive physics of coils fighting back. But I want you to think about this. The exact same violent inductive kickback that threatens to destroy our power grids is also the foundational physics we harness to power our entire world. Kind of wild, right? Next time, we're going to put real numbers to these magnetic circuits, solving some series and parallel problems. See you there.